Okay, maybe we'll get started with a sampling distribution question. Okay, so yeah, this week's lab is all about sampling distributions, and it is an important concept. So so let's start off. Maybe we'll turn this into a clicker question here. Okay. Okay, so we'll say in the population, and I'm making this up, but we'll say in the population, let's say that 32% of households own a dog. Own dogs, okay? And we will randomly select a random sample of 30 households. Okay, and so I'm going to ask, what is the approximate probability that this random sample of 30 households ends up I'm sorry, let me change this number, this random sample of 50 households. Okay, so what is the approximate probability that this random sample of 50 households ends up with 40% or more owning a dog? Okay, all right, let's, I'm going to put some answers in I hope this time one of the answers will be correct. Okay, so your choices will be 1131, 1587, 066, 08, 021. Okay, let me get the clicker software running. Start a session here. Okay, so go ahead and try this problem out here. All right, I'm going to hit stop here. So if you haven't clicked, be sure to click. Okay. All right. So let's see. All right, pretty good. Okay, we got 84% of you getting it right. Let's see. Let's go over the answer briefly here. So what we have is we say p hat, the sampling distribution of p hat. This follows a normal distribution. The mean of this normal distribution is going to be p, which is equal to 0.4. And then our standard deviation is going to be the square root of p times 1 minus p divided by n. Okay, and so let's figure out our standard deviation. This is going to be the square root. I'm sorry, not 0.4. What am I doing? Just kidding. The population proportion is 32%. Okay, so this is, we're going to put 0.32, 1 minus 0.32 divided by 50. When I punch this into my calculator, I get around 0.066. Let me just do this. I got 0.32 times 1 minus 0.32 divided by 50. Yeah, 0.06597. So yeah, I'm just going to round off to 0.066. Okay. So now if I create a little picture here, we're going to put in the center, we're going to put 0.32, and we're curious about being at 40% or more. So we want this side over here. Okay. And so we get our z-score, 0.40, minus the mean of 0.32. We divide this by our standard deviation, or sampling distribution, which later we'll call our standard error. And this, we get 1.21. We look up 1.21 in the z table, and the table always gives us the area to the left. And so that gives me 0.8869. That's this side over here. Therefore, this side over here is going to be 1 minus that. And so this area is area above 0.4 is equal to 0.1131. And there's our answer. Okay. I hope that's good. So this whole thing, the idea about the p-hat, distribution of p-hat follows a normal distribution, this is based on a mathematical theorem called the central limit theorem. Okay? So the central limit theorem is the mathematical I guess mathematical theorem, or mathematical idea that allows us to approximate the sampling distribution with a normal distribution. So, as far as our class goes, we're not going to try to prove this mathematically, okay? If you decide to be a statistics major, you'll take a course where you'll prove this, okay? But as far as this class goes, I just say, you know what? This is what happens, and we're going to just use the normal distribution from here on out because it's a good thing, right? Because the true distribution is a lot more complicated and it's a little bit more tedious. And so we say, well, there's this thing called the central limit theorem. It says the normal distribution works, and we're going to use this from here on out. Okay? We're not going to bother trying to prove it, but there's a few catches. Okay? There's a few conditions that must be true in order for this thing to work out. In order for us to use the normal distribution and answer these questions, there are a few conditions. Okay? So we do have a few conditions. That must be true if we want to use the central limit theorem. I'm going to just abbreviate it CLT, okay? And or if we want to use the normal distribution to approximate our sampling distribution. Okay, and so these are the conditions. It's like the terms of agreement here, okay? So number one, our sample, so I'll call this the random / independent condition. this states that our sample should be a random sample. Our sample needs to be a random sample. And the members must be selected independently. Okay, so if you see in the text of the problem, if it says, we selected a random sample, this condition is met. Okay, but if you decided to do your own type of survey or study, and you decide, well, you know what, I want to get opinions on, from the student body, and so I don't know, you go to some organization or whatever, and you just start asking people, how do you feel about blah 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 blah, okay? And you're trying to maybe you want to know what percentage of UCLA students, support whoever or whatever, okay? You decide to do a survey yourself. Chances are it's not a random sample, right? Chances are you're going to be running into people that are on campus, okay? That's going to exclude people who don't come to campus as much as they maybe should. And so, that's going to produce a biased sample, right? If you're going to walk around, if you're conducting a survey, I don't know if anybody would conduct a survey on Bruin-Walk, but maybe you're like, excuse me, can I ask you a question? You're not going to get a random sample, right? That's not going to be representative of the thing. So you cannot just take this intro class and say, well, I'm going to go out and do statistics. I'm going to ask people questions on Bruin-Walk and then do statistics based on my knowledge, because this requires that we have a random sample. So anyway, so that's condition 1. Okay, in textbooks it's easy to say, oh, we got to sample randomly. In real life, this is actually a hard thing to do. Okay, number 2, we've got the large sample condition. Okay, this means our sample needs to be big enough. Okay. And as far as, for categorical data, okay, this can either be so you must have at least 10 successes and 10 failures in your sample. Okay, so your sample, at minimum, must have 20 observations. Okay, the smallest sample that you could have would be 20, where you have exactly 10 successes and 10 failures. Okay, you must have at least 10 successes and 10 failures, or if you're not given counts, if counts are not provided, then you've got to figure out the counts yourself. Then both n times p must be bigger than or equal to 10. This is, n times p is kind of like your number of successes, right? And n times 1 minus p must be greater than or equal to 10 as well. Okay, and then the third condition, we'll call this our big population condition. This means the population must be big compared to your sample, okay? population must be at least 10 times bigger than your sample. Okay, or you sample with replacement. Okay, sampling with replacement means, you know, you take an observation, you look at it, and then you put it back in the population. So if you have you know, imagine you have a deck of cards. Okay, in the deck of cards, there's 52 cards, right? In the beginning, half of them are red and half of them are black. You got 26 red, 26 black, okay? If you draw out 10 cards, and let's say in those 10 cards, 9 of them are red and 1 is black, then what remains in the deck is you're going to have more black cards than red cards. And so what you have in your sample affects what remains in the rest of the population. And so that's a problem, and that's why your population needs to be big. What we're basically saying is that when you draw less than 10%, you know, what happens in your sample is going to have a minimal impact on the population, and therefore we can kind of ignore it. Okay. If you want to, the other way around this is that if you want to make sure that the deck is always half red and half black, then you look at a card and then you put it back. Okay, and then you can take a random sample of 30 cards or 50 cards. It doesn't matter, as long as you're taking one, looking at it, and putting it back. Then you're not altering what remains in the deck, okay, or what remains in the population. All right, so let's look at a few scenarios, and then I'll ask you if any of these conditions are violated. Okay. Okay, so we'll say the administration at UCLA decides to conduct a survey of its students. Okay, and I don't know, so I think there's approximately 28,000 undergraduate students at UCLA, something around there, okay? And then we'll say, you know, they send surveys to a random selection of 2,500 undergrad students. Okay. And then they get responses from 1,200 of those students that were sent surveys. Okay. And of the 1,200, responses, we'll say 400 answered yes to the question, whatever the question was. 800 answered no. Okay, so we'll start there. Let's make a clicker question out of this. Okay, so we'll say, were any of the following conditions violated? If so, which one? Okay, so A will be the random and independent condition. B will be the large sample condition. C is the big population condition. And D will be no conditions violated. Okay, go ahead and talk to your neighbors, see what you think. All right, and then I'll start the clicker running here. Okay, so let's see, and here. Okay, well, it seems we're in agreement that that this is not violated, right? So we have 28,000. 28,000 is over 10 times bigger than our sample. Okay. And then as far as the large sample condition goes, we have at least 10 yeses and at least 10 nos, right? So this is met at least 10 yes and 10 no, right? Okay, so it seems like we're in agreement that these are not violated. Okay, and the question is the random and independent condition violated, yes or no? All right. Well, it says that they selected a random selection of 2,500 undergrads, okay? The problem comes when we say they get a response from 1,200 of those students that were sent surveys. So if UCLA mandated, if they said, you've been selected for a survey, we selected 2,500 of you randomly, and then we're going to force you to answer the question, then it would be a random sample, okay? Then it would be okay. But because only 1,200 out of the 2,500 responded, there is some self-selection bias in here, okay? So, whatever the question was, that people may feel strongly yes or no about it, and that may be the reason why they gave their response, okay? And then the people who really didn't care to answer the survey or couldn't be bothered, they may differ from those who responded. And so the problem here is that only 1,200 out of the 2,500 responded, and we don't know if these 1,200 resemble those who did not respond, okay? If the non-responders resemble (1,200) who did respond. Okay, so this is because the survey was not forced. It is not truly random. Right. And this is actually a problem in real life that is almost impossible to avoid, right? So a lot of times you see results of surveys, right? We got, it'll say, this organization just released a poll and, 40% of people approve of this, right? And in general, you can't force people to respond to a survey, right? You call them up. Generally, most surveys are done via phone. You call them and you say, can we have a few minutes of your time? And if people say nope and they hang up, that that's you're not going to get a truly random sample. So, all of these are kind of hoping that that the people who respond are representative. A lot of work is being done to try to get as representative samples as possible, but it's they're still mistakes. Okay, let me yes.
Is there an acceptable response rate?
Is there an acceptable response rate? Not really. Generally, well, it depends, right? Like if you do an email survey, if you get over like a 3% response rate, that's like the best email survey ever. Because everybody just throws away their emails. Very, very rarely do you get. Well, I don't know. I guess it depends how large your thing is, right? So if you might email a group of 10 friends trying to organize, what day shall we go to the beach, and you still might only get like a 60% response rate. And these are like your friends that are actually invested in this this thing. So, and then as far as the rest of the world goes, yeah, people generally don't respond to surveys, right? Probably every time you go to Carl's Jr., they say, "Oh, take a survey, and you might get a free hamburger." And who responds to that survey, right? Who lets the fast food restaurant know how they're doing? You're going to get a very, very low response rate. So I don't know. Okay. Let's see. So anyway, we can check other conditions. Make sure you're aware of the conditions that we have to check. Let me, well, I guess I'll do one more example of, yeah, okay, so we'll do another scenario. I won't ask a question about it though, okay. Okay, so in this one, we'll say a company has, we'll say, 6,300 employees, and HR, the Human Resources Department, randomly selects 500 people for a survey. Okay, the survey is required, so all 500 people respond, okay? If you're a company, you can do that. And then we'll say, of those surveyed, we'll say 98.8% responded yes to the question. I don't know. Do you have a cell phone? Okay, so any conditions violated here? Yeah, which one's violated? Okay, so we have random and independent. We have large sample. C is big population. And D is no conditions violated. No, not a question mark. Okay. Without wasting any time, I'll just tell you the answer. Okay, so in this case, counts are not provided. Well, we can look at random and independent, and here it says they randomly select, so that condition is met. Okay. The population is 6,300, and our sample is 500. So this is so the population is 10 times bigger than the sample. But as far as the sample size goes, n is 500, and our p is 0.988. Okay? So n times p is going to be 494, but then n times 1 minus p is only 6. Okay? And we need at least 10 yeses and 10 nos, or 10 successes and 10 failures. Okay? So must have at least 10 yeses and 10 nos. Okay? So we have 494 yeses, but we only have 6 nos. So technically, this condition has been violated, and we cannot use the central limit theorem for our analysis. Okay. So we cannot use the normal distribution. All right, let me just finish with just kind of a few definitions, just as a reminder of how all of this fits in the big picture of statistics. Okay, so just here's our definition review, and then okay. So 1 week from now is going to be our second midterm, okay? And that's going to cover up through basically today's content. So next week, Monday is a holiday, so we don't have class, and then we have Wednesday. Wednesday, I'm going to start new stuff. It's called confidence intervals and whatnot. But basically, but Friday is the midterm exam, and that's going to cover up to everything we've done today. Is that okay? You guys look. So anyway, just wanted to give you a brief review of some definitions, because you will need to know this stuff. Okay. All right. So first of all, we have the population. This is everyone relevant to the research question. Okay. In general, this is too large to be studied directly. Okay, the sample instead is the selection from the population that we do observe. Ideally, it is representative of the population. Okay, a simple random sample should give us representative samples, but is not guaranteed to do so. Yes, question.
And then normally population is the same thing as sampling frame?
So when you do the sample, so ideally the sampling frame is the entire population, but in practicality, the sampling frame is often not exactly the same as the population. But so whatever deficiencies you have in the sampling frame will be the same deficiencies that will appear in your samples. Ideally, the sampling you can get a sampling frame, a list of everyone in the population, but practically speaking, it's really hard to do. Okay, we have parameters. Parameters are values or properties of the population. Okay, and so, we can, example is P. P is the proportion in the population with a certain trait. And then the corresponding thing from our sample is our statistic. This is the corresponding value. The corresponding value that comes from our sample. So in our example, we have p hat. So this is the proportion in our sample with that trait. Let me just write one more thing on the next slide, and then I'll let you guys go. So we have sample statistics will vary from sample to sample. And so the sampling distribution tells us about this variation. Okay. And then central limit theorem says you can use the normal distribution for the sampling distribution. Okay. And then the other part is that the accuracy of the sample statistic as an estimate of the population parameter depends only on the sample size. Okay, it does not depend on the relative size between the sample and the population. Okay. Have a great weekend. Stay safe out there in the rain, and we'll see you guys on Wednesday.